Hi, everyone. First of all, thanks for inviting me. I'm happy to be the application session for today. I'm also happy to have the last spot of today because at the end I will raise two questions considering the possibility of application of topological materials. And I would like to come in discussion with you about this, and I'm really looking forward to your ideas, if it's possible or not. First of all, I would like to start with the German innovation system because it's always about the money, and in this case, it's about where does the money come from that we can do our work. Here in the room, we are a lot of basic scientists, but when we start here, a lot of people come from Max Planck and the university. They have a scope of basic research, a lot of public funding, and on the other side, you have the industry. You have the economy, who drives their own R&D programs with a clear target to have good products, to have devices, how you can earn money out of this. So a completely different scope. And in Germany, you have three societies which are in between, which are Helmholtz, Leibniz, and the Fraunhofer Society. And Fraunhofer itself has more or less two basic tasks. One task is to help the industry to get their products, their devices better. And the second is to bridge the gap between basic science and the industry to apply maybe new materials, new concepts, new devices into the industry. And this is exactly our field of work. At Fraunhofer IPMS in Dresden, we work in the field of microelectronics, nanoelectronics. We have a clean room of approximately 1,000 square meters. And what we are doing there is we work on 300 millimeter wafers. So we work on full wafer scale. We do not work on coupons or something. We really have a whole 300 millimeter wafer. What you see on the picture here, there's a FOUP. There are 25 wafers inside, for example. And with this, we go through our clean room, through our facility. We own more than 50 tools, going from deposition to lithography, structuring, etching, and chemical mechanical polishing. And we work down to approximately 28 nanometer nodes. This is possible with our tool setup, mainly on 300 millimeter wafers. Our main customer, we are in Dresden. We have the lucky situation to be in Dresden because there are 4 fabs, really huge fabs, Global Foundries, Infineon, and X-Fab. Maybe next year Bosch will produce there. And Global Foundries is our biggest customer at the moment. They have more than 3,000 employees. So that we could claim that we know a bit how semiconductor industry, how the fabs work. And I take this slide here to start with limitation and demands from semiconductor industry. And I have chosen the thermoelectric materials, because this is the second field of work where I'm working in. I work also in thermoelectric infrared sensors. And what is plotted here is you have the thermoelectric figure of merit. Probably many of you have heard it. It's a kind of performance indicator for a thermoelectric material. And that is plotted over the years. And then you have several materials. It increased. And at the moment, you have bismuth being a very effective material for thermoelectric applications. And now these colors, orange and black, come into play because bismuth is not a CMOS-compatible material. In a CMOS fab, you wouldn't use bismuth. What does happen? You use silicon germanium, which is not that effective like bismuth. And what I want to say here is in the fab, not always the best material is used, but the most suitable material is used, because several things come into play. The material has to be integratable into the existing technologies, what exist in the fab. Contamination management is a very important issue, what I would like to address here. And also cost of ownership. It's always about the money when you work with the industry. CMOS-compatibility, what does it mean? It's a very difficult word, and when you go to different fabs, they slightly understand different what CMOS-compatibility really is. But for sure, it is a technology for constructing electronic integrated circuits. And the major advantages are low cost, fast manufacturing, volume production. So when you go in a semiconductor fab and you want to for example, introduce new materials, they first start with the contamination management. This I've tried to plot here. We work in different contamination classes. So what you see here are elements which are allowed in a fab, and they are classified into 5 classes where they are allowed to be or where they're not allowed to be. For example, copper is a very famous example. Where is it? Here. Copper is only allowed to be in one contamination class. In the other contamination class, when you build a transistor, for example, it's strictly forbidden because it would diffuse in a transistor, and in one transistor, 2 copper atoms would destroy the work function of your transistor. And it's also the other way around. When you are in the copper contamination class, other materials are forbidden. So what I want to say with here is that not every combination is possible when you work, for example, with copper. Yeah. I did my PhD at the Max Planck Institute in Dresden, working on thermoelectrics, and there you have the whole periodic table available to process good materials. In a CMOS fab, you do not have. This is really a big difference, so to say. What is important is that the materials have to be available to measure them, that they can be classified within this, and this restricts you to only a certain amount of elements. More. I think everyone everyone of you know Moore's law, that every 18 to 24 months the performance of an integrated circuit doubles. What I do like about this is I have collected a graph, and there's plotted several very clever people. At a certain point, they issue a prediction when Moore's law will come to an end. And for example, Gordon Moore himself stated in 1995 that his law will come to an end in 2005 due to economic reasons. What he meant was that it is simply too expensive for the semiconductor industry to buy new tools in order to do more scaling, to have lower technology nodes. But the semiconductor industry overcame this, and Gordon Moore in 2005, then he claimed, it will come to an end between 2015 and 2025. So a broad range. At 2015, he said the end will be 2025. So what I want to say here is Gordon or Moore's law is still alive. It's still working, but it will come to an end at some point. We do not know which point this will be, but it will come to an end. And one possibility to overcome this scaling, for example, Intel has now launched 7 nanometer node. TSMC has started risk production with 5 nanometer nodes. So there will be some technical limit at some point. And there is a term when you look in semiconductor roadmaps, which is called beyond CMOS, to go beyond this scaling. And one possibility is spintronics. One possibility is to calculate, to store information, to process information with a spin and not with a charge current. Let's skip this. When you want to do this, when you want to perform an all-spin logic, that everything is made out of spin, everything is calculated with spins, you have to overcome one very important problem. This is the propagation length of a spin, which is very short. Don't nail me down with the number, but it's somewhere below 100 nanometer, where the spin maintains its direction that you can store the information that you can calculate with this. For a charge current, it's different. It's much, much higher, of course. So what you need in order to do an all-spin logic, you need some device which can convert charge to spin and a spin to charge. Yeah, that you can store information, that you can calculate with spin, but the length scales have to deal with the charge current. So you need these devices. And I'm very happy that Mazar had this talk this morning, because he explained the spin Hall effect very properly. This is one possibility how this could be done. And so that's why I skipped this. What I want to explain a bit more in detail is a device, a concept, MTJ. Many of you know this, magnetic tunnel junction, where you store information with a spin. So a spin can have 2 different orientations, spin up, spin down. And in an MTJ, you have a tri-layer. You have a tunneling barrier, typically MgO, magnesium oxide, which is sandwiched by cobalt iron boron, so that you have two magnetic layers and in between a tunneling barrier. You can have, let's say, different orientation in the magnetic layers. You can have an anti-parallel orientation or you can have a parallel orientation. In the case when it's anti-parallel, you have a high resistive state, which means that spins cannot tunnel easily through the barrier. When they are aligned in the same direction, you have a low resistive state and the spin can tunnel easy through the barrier. And these are bits 1, bit 0. This is the heart of MRAM, which is a very famous spin-based memory at the moment. So it's illustrated here. This is the high resistive state. Spins are anti-parallel. When you do them in the parallel state, you have the low resistive state and the charge or the spins can go through it. One concept at the moment is that you adjust the spin here with the help of the spin Hall effect with a material underneath, which could be a Weyl semi-metal or some kind of topological material here. This is the concept in another sketch. This is called SOT, spin orbit torque. What Mazar meant in his talk before, in your introduction slide, there is another flavor of MRAM, which is called STT. And this is already in the market. This is a technology, STT MRAM, which is available, which is quite good. And the company Everspin, what you have mentioned, is at the moment the only one to really produce standalone MRAMs. They were visiting us last week. It was quite a very, very interesting discussion. So I want to focus on SOT. For this material, for this SOT layer, we have seen this this morning already. It's a pretty young field of R&D at the moment. So it started with gold, platinum, tantalum, tungsten. At the moment, tungsten oxide, which is used at the moment as a material. Predictions go for bismuth selenide, bismuth, or chromium bismuth selenide, which is not CMOS compatible. You cannot use it in the fab. So another possibility could be the Weyl semi-metals. So I skipped this one. I have screened the literature, or we have screened the literature, to several Weyl semi-metal materials which are available there. The gray intersection here are all material combinations where the element is CMOS compatible. So only going, putting the glasses of CMOS compatibility on and look if so these materials could be CMOS compatible. Then we watched if there is an existing CMOS compatible process for us. For example, growing big single crystal, cutting platelets is very hard work, like we have seen in Kevin's talk, but it's not CMOS compatible at all. So what result is that there are only 2 candidates out of these left, cobalt silicon and tantalum phosphide. One possibility to grow these is by PVD, by sputtering. We are in the lucky situation that we have an investment project running at the moment. We invest more than 40 million euros in new tools, and a big portion went to this tool, 4 chambers, 5 targets in every chamber. Do not want to bother you with the details. This is the photograph, how it looks like. Very handy footprint of 21 square meter of the tool. And this is how we want to start our work. And we want to start now on this SOT-MRAM. You see a sketch. Looks very simple when you consider here for this sketch which films you really need, you end up in 33 single films. Yeah, so this is written here in the TEM. Here you have 33 single films which are sandwiched on top of each other. And this is the first question what I have. How does the topological material behave in a stack? What does happen if the surface is stacked with an oxide, with a metal, or with something else, what has happened to the topological materials? This is to the topological properties. This is my first question, because it's always about stacks. In semiconductor industry, there is nothing open or something. Yeah? You have, for example, here, this is the SOT layer. This could be the Weyl semi-metal, and this is buried. This is buried with an oxide. There are here cobalt, iron, boron on top, and that's it. It's not open. This is the first question. Okay, when it comes to cobalt silicon, the nice thing, we have it available. We have it available in our clean room, so you can grow it easily on, this is single crystalline silicon, a wafer, there's oxide on top. Then you add amorphous silicon, a certain amount. You add a transition metal, cobalt, and then you heat it up, and you end with cobalt silicon. You see here in situ XRD, cobalt comes to cobalt silicon. You can do a TEM, and you can even do FTEM, and to see you have really a smooth cobalt silicon signal. Second question here is, when I have such a film, it's clearly polycrystalline. What does happen to topological properties if you leave the single crystalline state? Is it still topological? It's not. What does happen there? Is there, Jacob, is there any possibility to maintain the topological properties within a polycrystal, or do I always have to go for the single crystalline state? To only make it complete, I've shown STT-MRAM, SOT-MRAM. We also want to work on Racetrack with Stuart Parkin together. Similar concept with the MTJ underneath. There we work on the scaling. There we really want to scale the dimensions down to below 50 nanometers, only to make it complete. Good. These are the two questions. I've mentioned them. How does it behave when it has interfaces the material? What does happen if you have, or if you leave the polycrystalline state? A small group where we want to start with, very motivated young people, a lot of funding, and yeah, many questions. Thanks for your attention.